All right. So one thing, I want to mention a couple of things before we kind of jump into things here. So the first is, and I had to copy and paste this to, there it goes. If you're having issues with Stata, try to make sure you've got this working because I'm going to start using it even today. So I want you to be able to follow along and kind of open the files and work along with me. I'll walk through it very slow today. So if you have to kind of, if you don't have it quite going today, it won't be a huge issue. I think a lot of people, some of the issues result in like settings that aren't allowing the Citrix app to do certain things. So don't worry about reading this right now. I just got it copy pasted here for the sake of my own sake. There's like two usual like sus or culprits that we can kind of resolve in terms of how your computer is like allowing Citrix to operate. So it's through like the settings. You just have to like give it permission or use the light version is one of the ways. The other way is like assigning file types to these ICA files. So I can kind of help you with that after class if you're still having issues. Walk through kind of these. I just brought them to class, so I make sure I have them with me because I don't have them memorized exactly what those solutions are. Another really easy one, and I think I put this in an announcement, is it sounds really stupid. Sometimes using web browsers other than Google Chrome can help resolve the issue. For whatever reason, Google Chrome has like the most restrictions in terms of like default settings to different things. So sometimes it's as simple as that. But if you're still having issues with that, like I said, we should have a little bit of time kind of after class to hang around. I can kind of help you resolve those because we'll really start hitting the ground running with that next week. Okay. So we'll start out today. Also, I put up, this is not for any points, but it helps me get an idea kind of where you guys are coming from. So it's a little background survey. So I think I have it set to be the end of the day. What, 19th is going to be Sunday? Yeah. So if you could get on and just fill that out once again, it's not tied to points. So this is really just for me, help me cater this class to you guys. And also just to kind of get to know you a little bit better in terms of the makeup and demographics of this class. So you'll see that up on Canvas on the homepage now. So if you get on and get that done before Sunday, I would appreciate that. Next week, every single, from here on out, I don't do it the first week because there's still a lot of ad drops, things like that. Next week's, starting Tuesday's class, any class period's fair game for me to use those in-class quizzes on Canvas, okay? Where I kind of manually deploy them and then close them out so that, you really only know when I'm using them if you're here. And also, I might help you out if you are here on what the correct answers are, okay? Any questions for me before we dive into material here? Once again, I know we're supposed to have 45. I'm getting a little bit worried, but okay, I guess. So just some review of some things that I'm going to start using a lot. You're like, what is it? What am I writing? So we're going to be using summation signs a lot when we're looking at different things. So even calculating means, we'll already start using the summation sign. So the way that we read this summation sign, this Greek letter sigma, is starting with I equals 1. Now you can do things other than I equals 1. For this class, I can't think of off the top of my head anything we're going to do that isn't the case. But basically, starting with the very first observation in a data set, right? So if we have a data set, maybe it's students and what their current GPA is, starting with the first person in that data set, go through and take their, start there and then go all the way to the very last one. Now here it's only 5. Right, so it'd be like 5 people in my data set. But a way that you would read this if you didn't have it in data is if I take the summation sign from 1 to 5 of the value 2, what that means is put a 2 down for that first one, go to the second one, add to it 2, go to the third one, add to it 2. I'm just adding the same value 1 to 5, so adding 2 to itself basically 5 times. Okay? So that would be like and we're not really going to use that, but that would be how you read the summation sign. In more general, with data, or this random variable where we have information collected on some random variable y, start with, so this subscript is kind of identifying this is the value for that y variable of the first observation. So start with the value for this variable of the first observation, add to that the value for the second observation, add to that the value for the third, all the way until you get to the value of the, what did capital N represent last class? You remember? Observations. The total number of observations in a population data set. So go basically all the way to the very last observation. Okay, so that's all the summation sign means. All right. Any questions? Hopefully this is looking somewhat familiar, like I said, from 370 or an equivalent. You've probably also talked about measures of central tendency. So the easiest one, I think we use, see this in publications on CNN and everything, is the mean, right? Now we'll call it the expected value because we can do this even if we're dealing with not a collection of numbers, but a collection of values that we might see and their associated probabilities. So we won't call it always the mean, but we'll typically the more formal term of this is expected value, okay? So we'll use kind of mu here, kind of representing that Greek letter. This is going to represent our mean. How do you calculate a mean? So in layman's terms, if I gave you a set of 5 numbers, how would you find the mean of those 5 numbers? You are in the wrong class if you don't. Yeah. Yeah, you add those numbers up and you divide by 5 or the number of numbers you have. That's all this is saying, right? That summation sign says go through every single value you have for this variable, these 5 numbers here. In my example, n would be 5. Add them all up, whatever they add up to, then divide that by the total number of numbers that you have. Or here, when we're looking at a data set, when I add up the value for every single observation, I'm dividing by what's the total number of total number I have, the total number of observations, right? Or that population kind of number that's in the population data. Okay, so nothing too crazy here yet. Now, if we have different values we could see, so maybe I don't have a nice easy data set. I said, here's this variable, and I know it could take on these 10 different values. Each one, some of them are more likely than others. So if I have different values that this variable could be, and they have different associated probabilities, how would I find the mean of these random variables or that have these associated probabilities? I would go through, so E kind of brackets Y, all that's telling us it's the expected value of this random variable Y. So that's kind of what that, I don't know, syntax or, what am I looking for? The notation, right? That's what that notation means. Find the expected value of this random variable Y, go through every single possible value for this Y variable. So YI is still the different values you could see, but for every single value, don't simply add them together now, add them, take that value, multiply it by its associated probability. And then once you add those up, that should give you the expected value. Well, I don't think I have in the slides here, so we'll go off here. I'll kind of, so if I think about the switches, there we go. So if I have these probabilities associated with seeing different values of Y, why doesn't this look like our typical kind of mean, right? This is our usual equation for a mean. When we're finding an expected value, where's the denominator gone? Well, if I think about this, if I were to add up every single value of Y, the probability I see something, let's say that out of 100 observations, 10 of them are the same value. What would the probability I see that value be? So I got 100 observations, 10 of them, let's say Y is equal to 39. What's the probability if I select one at random, I see 39? Yeah, 10 out of 100, right? That's the probability. So 10 out of 100 would be a probability of 0.1. So what are you really doing there is you're kind of like, instead of multiplying by the probability, the number of observations you see take on that certain value divided by n, right? So this is the same as the probability you see that number, right? 10 over 100 would be the same as 0.1. So when we're using probabilities to calculate expected values, that n is kind of like floating on, behind the scenes there, right? It's just that when we calculated the probabilities, we already used that, right? We already used capital N, or the total number of observations, to determine what those probabilities are. Okay. Any questions on that? This is looking somewhat familiar. Okay. All right. So the next thing we'll talk about, another measure of central tendency, is the median, right? So all the median is going to be is it's the value where 50% of the data is below it, 50% of the data is above it. Now, when I say above and below, that means in terms of if I were to order them from smallest to lowest, or sorry, smallest to lowest, smallest to highest, right? Or smallest to largest, okay? So what is the median going to be less influenced by? So let's say I've got a set of 10 numbers, right? So we'll could even do this real quick. So let's say I'm going to make this math easy on myself. So 2, 4, 6, 8, 10, 12. Well, I'll just do 6. So make it easy, right? So I add these up. I get what? 10, 10, 10, 30. Nope, I'm going to make this even. I'm going to keep going. What do I want this to be? I'm making this easier on myself. Let's do 5s. 10, 5, 15, 20. All right, we'll do 4 numbers. So what would the mean be here? So we add these up. We get what? 50 divided by 4. So it's going to be what? The mean would be 12.5, right? Now, actually, I'll make this easier for us. So let's do, I've got 20, 20. So let's do 25 there. So now I add these 5 numbers up. I get what? 75. So 75 divided by 5, I get this mean of 15. Okay. What would the median of this data set be? What value here would 50% be of my observations be above and below? Yeah, this one right here, right? So here I've got a nice symmetric data set where the mean is exactly the same as the median. Now, let's say I've got a very similar data set. What do I want this to be? Let's do 150 here, right? So I now have one extremely large value. If I were to find the mean of this data set, if I'm looking at this correct, it would be what? 200 divided by 5, so 40, right? So notice that one extreme observation pulled the mean up quite a bit, right? What's the median of this data set? Excuse me, still 15. So the median is not going to be influenced as much by extremely high values, or what else would influence the mean? Not just extremely high, extremely low values. We have a different example, right? So the median sometimes is a little bit more reliable on really where the middle point of that data is, especially when we're dealing with really small data sets. The larger the data set, any one observation isn't going to influence the mean as much, right? In fact, if you want to think about if I had not probabilities, how much is each observation influencing this mean? You could really think about this as just rewrite it as y times 1 over n. So the higher the number of observations, the less influence each observation is going to have on that mean. Okay. Any questions? This doesn't look like 15 at all. Sorry. 15 here, right? Any questions on that idea? Okay. So we've got 2 different measures of central tendency. We've got a third, which we won't really use a ton, but we just want to be, acknowledge what it is, which is the mode, right? So you remember from 370, the mode is just going to be the value that occurs the most, right? So it's going to be the value for that variable that shows up most often in your data set. So for some variables, this makes sense. We'll quite often have a mode. For smaller data sets, and let's say I was measuring something like individual income, what do you think if I had like 100 people, what do you think is going to be true about the mode for that data set? If I have their income for 100 people, I measure it out to the second decimal, do you think anyone likely has the exact same income? Probably not, in which case the mode would be everything happens once, we really don't have one. So for smaller data sets where we have more continuous variables, this isn't going to be real useful, right? Now for larger data sets where we have like discrete variables, so maybe I have data sets on a household and the number of individuals in that household. Well, the numbers we're going to see there are going to be 1, 2, 3, 4, whatever the Duggars or the largest family have, all right? But primarily we're going to see like, a smaller set of values. It's likely we're going to have a mode there that actually gives us some information about the data set, okay? But larger or smaller continuous data sets, it's not as useful, okay? So the other thing, if we can figure out what the middle point of the data is, we also want to know how varied is the data, right? So we have a couple measures of this that we're going to use a lot in this semester. The first is going to be the variance. So sigma squared here. So this is going to be, lowercase sigma, so don't get it kind of confused with our uppercase, but it's lowercase one. What is that? How are we going to calculate the variance? So what we're going to do is go through every single observation, take the value for, once again, we're adding up whatever is to the right of this summation sign. So for the very first observation, take that first observation's value for y, subtract the mean, take that, what we'll end up calling the deviation from the mean, right? It's that value's deviation or difference from the mean, and square it. We then go to the next observation, take its deviation from the mean, square it, add that in. Go to the next observation, take its deviation from the mean, square it, add that in. Go through and do that for every single observation. And then similar to the mean, we then divide by the total number of observations in our data set. So this is going to pick up how much each observation is kind of varying from that middle point of the data, right? We're looking at the deviation from that mean. Okay. Once again, is this hopefully looking familiar, right? Now, because we're squaring things, what's going to be true about every deviation from the mean once I square it? It will be positive. So if I'm adding up only positive values, what has to be true about my variance? It's always positive, right? So our variance will always be positive. It's also going to do something because we're squaring that deviation. Things that are, say, I'll give the extreme example, 1 away from the mean. When I square 1, it is still 1. So it only adds 1. Well, what if I'm 2 away from the mean? Well, now instead of adding just 2, I would take that deviation from the mean of 2 squared. I now add 4 into that numerator. If I'm 10 away, I now add just 10. I add 100. So data points that are further from that mean, our variance kind of over penalizes the data, the calculation of the variance for that, right? Because by squaring it, right, 1 becomes 1, 2 becomes 4, 10 becomes 100. Right? So our variance is really going to over penalize these extremely high or extremely low values in our data. Okay. So just to kind of make that point, I won't go through and calculate the actual numbers. But when I'm looking at like similar data sets, even if I had like 100 numbers here, these, other than the last observation, these two data sets are identical, right? So if I calculate the variance, you might think it's going to be pretty similar. The problem is, because there's this extremely large value here, if I were to go through and calculate the variance for this data set, it's going to be significantly smaller than the variance for this data set, because that variance is going to capture the fact that there's one data point that really varies from that middle point, right? And we don't just want to throw that out, right? That's part of it. We should be using that information, right? That there are observations that exist that vary a lot from this middle point of the data, okay? All right. I might be going through this a little bit slower than I should, but I think it's good to get a good base here. We can do the exact same thing, but for like an expected value. So if we wanted to calculate a variance for a random variable y, I would just go through, add up the deviation of every single possible y value from the mean squared. So it looks very similar to what we're doing up here. It's just now every y value has an associated probability with it, right? So I'm going to take that deviation from the mean squared and multiply it by the probability I see that deviation from the mean, okay? And I've got a little toy example here in a second where we'll work through an example and see what this would look like, okay? And then my standard deviation, do we recall, if I have my variance, how do I get my standard deviation? I just take the square root, right? So it's just a different measure of the variation that exists in the data set. It's a little bit more, it's going to have more uses for us when we start to calculate other statistics, which we'll even see today. So a lot of the times we're going to want to scale that variance and just take the square root, and that gives us what we call the standard deviation, okay? And using this kind of sigma squared and sigma, oh, yeah, there it is, sigma. These are kind of these Greek letters. You can think about, other than like the capital N, which kind of goes against this, but for most statistics, the Greek letter is going to represent a population statistic. So when we're looking at mu, this was going to be Greek letter that was the population mean. If we look at standard deviation variances, sigma, this is going to be a Greek letter. This is the population variance, population mean. We'll talk later on what, how we notate the sample variances and sample means once we get there, okay? So let's say I had a random variable that looks something like this. How would I calculate both the mean and the variance of this random variable? Okay. So how would I calculate the mean first? So I've got 12 different possible values that I could see here. Maybe this is like the number of people in a household. Can't see 0, so that kind of lines up with this example. And based off my data set, I don't see any that have like 10, 11, or 12, right? So it's somewhere in between. So how would I find the mean of this data set? If you were entering this into a calculator, what's the first number you would put in?
Add all of them.
So that's what I would do if I didn't know that if these were actual data points, right? These are different values for y, and I know that seeing 1 is not as likely as seeing 4. So I want to incorporate the fact that seeing 4 is more likely than seeing the value of 1. Okay. So what I'm going to do, yeah.
You find all the values, probability greater than 0, by the probability.
Yeah, and I could even do the ones that have a probability of 0 in case things change later on. So what I would first do is say, look, I know this X value, and I'm going to cheat here so I can write these down. Oops, nope. I want this to be there. I just want to be able to see this. So here we had the probability that X is equal to these different values. And I'll just start out with a few of them. I won't do every single one just for the sake of time, right? And we kind of had all these different values, right? Technically, what I would do is start with the first value, right? I should be taking every y value, multiplying it by its associated probability. So 0 times 0 plus 1 times 0.06 plus 2 times 0.03 plus 3 times 0.2, all the way until I get down to that very last possible value I could see in the data set. That would give me my mean. Okay. So show you another way of doing this. First of all, are any questions on this before we keep moving? So I won't expect you necessarily to use, although if you have the capabilities, I would suggest, especially for something like this, it's great to enter this into a calculator. I very likely could make some mistakes. So if I had this, I might copy and paste that. Oh, hold on. There we go. I'm going to copy and paste that into Excel. Well, I know that to calculate the mean, what should I do? I'm going through every single value for y. I'm multiplying that by the probability I see that y value. Okay. I'm then going to make sure I do that for every single possible value. And if you're not super familiar with Excel, we're not going to go through a tutorial on it, but this is basically a very quick way of coming up with all those values. Whereas if I'm entering this into a calculator, I'm bound to make a typo, right, at some point. This isn't going to make us a typo for us. Now, once I have every value multiplied by its probability, what do I want to do? I want to add all those up. So in Excel, that's our sum function. We'll see later on today how we do this in Stata, even a little bit easier even than doing it in Excel. So I get what? 5.12 is going to be my mean. Okay. So if I've now got my expected value or my mean of 5.12, how can I calculate the variance of this random variable y? So what's the first thing I'm going to do? Well, we remember, so I've got the deviation of each value from the mean squared multiplied by the probability I see that value. So the very first value is 0. Subtract that mean of 5.12, square it. Now here, really don't have to do this one because what's the probability I see 0? 0. But just to be complete, if this did change in moving forward. And then I would add to that the next possible value for, and I put x here, sorry. The next possible value for y, which is 1 minus the mean, square it, multiply it by the probability I see that deviation from the mean. And then add to that the next possible value minus the mean squared multiplied by the probability I see that value or that deviation from the mean. Okay. Any questions on this? Is this looking You've seen some of this stuff a little bit before, okay? Now we could also do this pretty quickly in Excel. If you're not sure about freezing, don't worry. I'm just going to freeze this just to show you you can do these calculations relatively quickly. Whoops. So I'm going to take the deviation of this value from the mean, square it, multiply it by the probability I saw that deviation from the mean. I'm then going to do that for every single possible value. And then once again, add them all up. Here I get a variance of about 5.4. Okay. So this is how we calculate means, variances. We can do it by hand, right? Maybe on the quiz, I might ask you to do something like that, right? We can also use Excel, and we'll see later on, we can use Stata to do all of this behind the scenes for us. So we don't have to worry about taking the time to copy paste this and do this line by line. Okay. All right. Oops. So that was kind of the work we just did there. We'll go through this a little bit quicker because we're not going to ever be calculating these by hand, but we'll kind of see if we can get them from Stata. So we also talk about things like skewness. So the mean is like the first measure of central tendency. The variance is kind of the next the next level or the second moment, what we call it. The skewness would be what we call the third moment. I'm not going to expect you to, I'm not going to use this term a lot, but basically it's a way of capturing the fact that even though there's variation to this data set, we want to know which way do we see the most variation. So do we see more extremely large values or do we see more extremely low values? So when we go through and calculate skewness, we'll take that deviation from the mean, but instead of squaring it, we cube it, and then we scale it by, if we were to calculate kind of a standard deviation to the third. Once again, we won't do these by hand, so don't worry too much about exactly how you're calculating this, but know that if I take something to the third power, once again, 1 times 1 times 1 is still 2 times 2 times 2 is now 8. So it even more so kind of penalizes the extremely low, high or low values. And also when I take something to the third power, what's now true? My values I'm adding in here could be negative, right? So skewness, we can have positive or negative skew. Positive skewness is going to exist when we have extremely large values that are above the mean. Because when those values are above the mean, it's going to be a positive deviation, positive times a positive times a positive. That's telling us that if we have a positive skewness statistic, there's more observations that are extremely above, extremely far away, but above the mean. If there's more of those observations that are extremely, far away from the mean, but below it, well, then we have negative deviations. Negative times a negative is negative. That would be why we call this one with a longer left tail negative skew. Right? So longer right tail, that's going to be representative of positive skew, or we have extremely large values on the right-hand side. Extremely long left tail is going to represent negative skew, or we have some values that are extremely far below that mean. And if we end up with something where we have the mean being exactly the same as the median and happen to be exactly the same as the mode, that's what we would call a symmetric distribution. Any questions on this before we keep moving here? Okay. All right. I won't waste a lot of time on this. We'll talk more about this in subsequent kind of, I guess, not really chapters, but in subsequent classes. But after skewness, you can go to the fourth moment and talk about kurtosis. So even if I have 3 perfectly symmetrical distributions, right? They're like, symmetrical means, right? If I take the mean and I fold this distribution on top of itself, it exactly matches up. That wasn't true when I had skewness, right? Those don't match up. But when they're symmetrical, they do. So even if I have symmetrical distributions, I still might be interested in what, are there more observations that are centered around the mean as opposed to far away? Because when I'm calculating things like skewness, if they're on either sides, they kind of cancel each other out, right? Because one was negative, one was positive. So kurtosis is a way of measuring essentially how fat are the tails of the distribution. and how fat the tails are. What is that telling us? Well, what's on our y-axis here? So these are different values for our y variable. This y-axis is going to represent probabilities, how likely it is we see these different values. All the values that are close to the mean, those values are a little bit more likely than values that are further from the mean. But if we have a lot of kurtosis, right, that means that values near the mean, yes, they are more likely, but that probability is relatively low, and seeing values far away still has a relatively high probability compared to a distribution that has relatively low kurtosis, right? Here, or positive kurtosis or positive or negative. So I won't necessarily kind of quiz you on that. This is more just a kind of review that we can calculate statistics that give us some measure of what the distribution of these different variables look like. I'll primarily want you guys to focus on the mean and the variance for right now. But when we start to look at output from Stata, we'll see that we can get these measures as well. Okay. You probably didn't talk about this one, did you? Has anyone seen this before? No, yeah, this one's not as common. So we did kind of the Stata introduction last class. Where are we at in time? Well, we'll do this real quick. So, well, no, we'll hold off. We'll kind of come back to this. So let's jump over into Stata here. We'll get a little bit more kind of look at how we actually use this program to work with data. We'll look at some of the things we've already talked about, and then I'll kind of use it to introduce the next type of statistics we might want to calculate. So I said last class, if you have already, and a lot of the times as the semester progresses, so really after this like first 2 weeks, I will be giving you what are called .dta files. Those are just data files that you can go, file, open, and you can open these Stata data sets, right? They're already in the right format. Sometimes what we have are, so I've got a CSV file, I believe. We look here. That state cigarette tax, it's a .csv, so it's not in the correct format. But that doesn't really matter because we can import a CSV file and it will convert it into a .dta file. So I'm going to go to File Import. Going to go to my OneDrive where I've downloaded those files from Canvas, or you have downloaded those files from Canvas. So week 1, here's that state cigarette tax file. I'm going to go to Open. Now it gives me a preview of the data. So I've got a bunch of different states, cigarette taxes, packs per capita, a bunch of different variables, right? It's kind of cutting this off a little bit. I want you to be able to see it, and I don't think I'm going to be able to because I can't. There it goes. Well, I didn't want that, but we'll hit OK there, and it should. There we go. Oh. So I can import it, right? And now it's in .dta. So now when I go to this web browser, or what, not web, data browser, now I can see, okay, it took that CSV file and it converted it into a stata.dta file. Now I can start to work with this data, okay? So once again, you don't have to worry about what the exact code is because it is user-friendly in that you have an interface up here. You just go to File, Import. We're choosing the type of file we want to import here, which was a CSV file. And then I screwed the window up. There we go. And then just selecting on this folder so that I can go to my OneDrive, find where that file exists, and open it up. Okay. This is where I'll stop. Yeah. What do you mean? What's it tell you?
That no, I didn't match my search, but it's in the CSV like format, but it doesn't appear.
Yeah. So are you going through File Import, or are you trying to go to File Open?
File import.
So if you go to Import, you go to CSV. You go to your OneDrive, right? Or are you trying to do this from your desktop? It's not going to work, right? So it can, because you're using Citrix, it's kind of operating off of your IU account. It can operate files that are in your OneDrive. Yeah.
All right, somebody that might help because if this is if you download because you're on a Mac, right? If you download the file to your downloads and then you go right there to your OneDrive, you can drag the file from your desktop into Citrix and it'll put it into your OneDrive. And then it'll go from there.
So, and that's fine. I would get in the practice of downloading all the files to your OneDrive.
Yeah, it'll save.
So ultimately it'll be in the same place. Yeah, yep. But you can do it that way too. I always just starting out the way I'll kind of do it in class. I'm just telling you is if I'm doing import, I'm always going to access my OneDrive here because I know I've got the right files. Yep. So you have to kind of open these through your OneDrive because you're not using like the actual program. You're using a program from the cloud or however it works. I'm not the most tech savvy person, but I understand, I just know that you can't operate it because you don't actually have Stata on your computer. You're using like a shared license. Yep. Any other questions at this point? Any other problems we're running into? Yeah.
It just says when I click on download that like this operation is can't with these restrictions.
Downloading the
Yeah.
file from what?
Like if I click on download on
So once again, you can't take anything from your downloads folder, right? When you go to this file import, you need to be importing files. Notice I didn't go to downloads, right? So this is the error you're getting.
Yeah.
So where do I need to go? Anybody want to help me out? Yeah, I have to open these. I have to download them first. So once again, to make it easier, if it's easier to go to Canvas and download them to your computer and then drag them into your OneDrive, now you can open those up from your OneDrive. Like I said, there might be a workaround where you can do it from the Stata interface. It's probably going to be a little more self-explanatory and easy if you just download them to your computer, drag them over to your OneDrive. Okay. So once they're in your OneDrive, then you shouldn't get that error. Any other problems we're running into? Okay. So how many of us have this open? Decent amount. How many of us are still having issues? So what are the issues?
Stay like 2 minutes.
Oh, you're fine. No, you're fine. I'm just saying, are you getting like anyone getting errors or anything like that? Okay. So moving forward, I'll have these files up before we start using them in class. I would try to have them downloaded from Canvas, especially later on the semester. Some of these files are going to get a little bit bigger, right? So if we try to do it here in Ballantine, the Wi-Fi sucks and it might take a while for you to download it, right? So I would really try to have this done before you show up to class because the Wi-Fi in here and downloading these larger files isn't going to be ideal, right? Do you have a question? So the only other, if you can't get it into your OneDrive, make sure we talked about last class. One thing that you also have to make sure is that we go to, oh, no, that's not what I wanted. So if we go to 1.iu, we go to cloud storage. We need to make sure that, well, I'm not logged in. But if you don't, oh, come on. Right, you need to make sure that you have your OneDrive authorized through cloud storage. Do not use you need to make sure that IU OneDrive one is the one that's authorized. Yep. Anyone else hearing some murmurings? Anyone else running into any issues here? Or at least no one that wants to speak up here. Do you have any issues? You good? Yeah.
Yeah, you can tonight OneDrive. Just look up OneDrive.
So once again, I think getting this authorization. So I mentioned this last class, making sure that you go through cloud storage and making sure that this OneDrive IU is authorized. It should then allow you to see that kind of pop up as a file path when you're pulling open, say, a file explorer, right? For sometimes, so for example, I don't know why this computer does it this way, like my personal computer doesn't, but notice it shows a OneDrive here, but like it's not set up. a lot of the times you can find your OneDrive under your kind of PC and it's already kind of authorized there. So that might be another place where it might be hiding, is under that kind of PC icon. Oops. Except for now I'm clicking on things on accident. And then this is where you would want to drag and drop those downloads. Yep. Okay. And we can kind of workshop some of this. Like I said, hopefully we'll have a little bit of time kind of at the end of class here. Because I want to try to at least walk through how we use some of this once we do get it using. And if you want to take notes in this part, if you haven't been able to kind of get it open, next, like I said, we'll try to get those ironed out here. If you're still having issues, maybe even office hours, sending them an email, trying to get that worked out so we can start using these in class and following along. Okay. All right. Any other questions at this point? So we can open up .dta files, we can import other files. Now, remember I said, this is the actual code that imported that file. Now I can do it all from the interface and that's fine, right? But it's likely that I want to save this somewhere. So where do I save that? What did I call these on Tuesday? Do we remember? Do files, right? So I can pull open this little do file editor. Now I'm not going to start from scratch. I've already given you one, so I'm not going to make you like type feverishly every single class, right? I'm going to give you the code that we're using, and we might add to it, right? But I'm not going to make you kind of start a completely new document, although that's what you would do when you're starting to tackle those problem sets. So once again, I'm going to go down here to my OneDrive. I've got this review of statistics do file, which was on Canvas, which I already downloaded and dragged into my IU OneDrive. I'm going to click on that, open it up, okay? So I now have all of this code that I've already typed out for us. Now here's where we get some kind of weird things as well, right? So notice I had the code of like import, delimited, and this file. If I try to run this code, so just like I put the code in here, it opened it up just fine. We just did that, right? If I try to use this do file, and I select the line that I want to run, and then I go up here to execute that selection, I'm going to get some red text, which means that I made an error, okay? So why did I make an error here? Because I'm trying to open something. I wrote this file from my desktop computer where I actually have the program. So for all of you, you don't actually have the program, you're going to be operating off of your OneDrive. It probably makes a little bit more sense to do this, okay? So here, when you go to the file import method, it puts that code in for you. It tells you kind of what your OneDrive file path is. Now, mine is in like all of these folders. So for you, this might not be as long. This might be you create a folder that's E371, and that's all you have here. I've got mine under Spring 2025 materials in this folder. So where that state cigarette text file is at on my OneDrive, I need this entire file path. Once again, for you, I would just try to create like one folder so you don't have a bunch of them. So you always just have like the same file path, because what I can do is I'm going to copy this, go over to my do file, okay? And I think I have it down here, but for the sake of what we're doing right this second, if I can remember the syntax here, I don't want to get it wrong. Where's it at? Yeah, okay. So I'm going to paste that file path into Stata. Now, before it, I'm going to type this word global path, okay? So there's a space in between. What I'm going to do is then put, oh, what is happening? Hold on, I must have accidentally got a key stuck here. Give me 1 second. It's not what I want. Oh, gosh. All right, let's try this again. Okay. Oh, I see. It is stuck. There we go. Can't hit that key as hard, I guess. So I'm going to put kind of quotation marks around that file path that I just copy and pasted over. Like I said, for you, hopefully that's much shorter. Right? Now, instead of trying to open this from my desktop, it's now going to try to open this from whatever file path I've set as the global. So now I'm going to want to use the exact same kind of line of code. But instead of all of this, right, the file that I want to open is this state cigarette tax CSV file. However, where does that file exist? It's on my OneDrive under this file path. So there's these things that we can assign in Stata, and really the only way we're going to use these is just to open files. You can use them in incredible ways, but for us, we're just going to use these global variables to open up files. So I'm setting what is called a global variable, which is anytime I put in this word path and I put it in these squiggly brackets, that's going to say, okay, use whatever I've told Stata that word path should mean. For me, that's going to be this text, right? Or that file path where I'm trying to open files from. So now when I run this code, it should import this state cigarette tax file, and it knows where to find it. I don't have to go through the file. Now, by all means, you can go through file import. You don't have to set it up this way. I'm just showing you how to do it this way because a lot of the code I'll show you the rest of the semester, I use this global path a lot because I'm going from this computer to my personal desktop to other classrooms, which will look slightly different sometimes. And so I want to make sure that I know that I'm working off of this computer's or the iDrive when I'm using it for you guys here. So this will be my global. I'm going to go ahead, run these 2 lines of code. So I'm going to hit execute here. I've got an error. What isn't it like? Oh, I know what it is, maybe. It wants, let me see, what did I set wrong here? I think it's a backslash. String global path. Oh, I see. I forgot this. Sorry. It's squiggly lines and there's a $sign in front of it. I forgot that's added in that syntax, right? So $, and then in squiggly lines, this path. Now you can call this whatever you want. I'm just going to call it path because that's the file path we're trying to use. Now, if I do this, now it should open it up just fine, right? So notice I don't get any red text here. I go to my browser. Sure enough, there's the data. Okay. Any questions on that before we keep moving here? On time.
Is there a way to find your path? Like,
To do what?
can you write something in there that'll find your path to somewhere?
No, because it doesn't know what file you want. It doesn't know where that file would exist. So it's not a perfect way. You can go to like here, you can go and you can see like what your file paths are. To me, the way I honestly personally do it, the easiest way is the very first time I start working on a project, I do it manually. And then because I know the manual way identifies where that is, I just copy and paste it from there. Because that way I know I'm not going to make a typo. I'm not going to be copy and pasting something that's not going to be the correct file path for it to open up on the computer I'm on. So that's how I would do it. And once you have it set once, like I said, if you keep using the same folder and just put all of the files in there, you can keep using the same one over and over and over again. Yep. Any other questions before we keep moving here? So a couple things with this. I've included something that's kind of important here, which was that comma clear command. Once you start opening up, and this won't play a role too much for you guys because mainly you're going to be dealing with one data set when it comes to these problem sets. But if you try to run this code now, it says no, the data is going to be lost. It tries to prevent you from just dropping data, like make sure that you save it. So the override command for that was that comma clear. So it clears out whatever was open and it now imports this new file that you want to use, right? But once again, I'm not going to expect you necessarily to always know how to do it. You'll have a do file that looks like this that has the syntax you should be following. And a lot of the times you can get this code by simply file open or file import. You don't have to go through and manually kind of do all of this, okay? So once we have that data set open, I've now got different years, not countries, states. I've got what cost per pack of cigarettes, the state tax per dollar, a bunch of different variables. So I can start to do things like manipulate my data set.
How do you do data set?
Yeah, so we went through this last class. So there's,
No, like, you kind of like fold it up to the side and you.
yep. So there's two icons here, right? One is data editor, one is data editor edit, one is data editor browse. I said it's probably best to always use data editor browse so you don't accidentally like type over the data, like, you know. But yeah, that gives me a new window where I can actually see what data I'm working with. Yep. So, and then I just click on different windows, right? So now I'm back to my do file. There's this variable that I can see exists, which is what? Oh, it's right there. No, have to scroll. Location ABBR, which is the abbreviation, right? Or if I was looking at the data, it's the actual state abbreviation, right? So the two-letter kind of abbreviation. So what I can start to do, if I download a data set, sometimes the variable names, based off of whatever format it first came in, are gonna like be really messy, like location ABBR. I'm like, what does that mean? Sometimes it's like less clear and it eliminates spaces when you're doing variable names. So I'm just gonna call this variable, I'm gonna rename it. So we're gonna start using commands in Stata. Anytime you use like a pre-built-in command, it'll show up as, it might be kind of hard to see, but this is blue. Does it look blue to you guys? Yeah. Okay, it's hard for me with the light coming in. But it basically says, okay, this is a function that's already built into Stata that tells it, take this variable and just rename it with this new variable. I'm gonna call it state. So I'm gonna highlight that code, run it. Notice in the actual program, it ran that line of code. And now if I look at my data set, that first variable is no longer location ABBR, it now is called state. Right? So we can do things like rename variables, very simple, right? I could rename other variables, right? And I wanted to make this point. Let's say I've got the second variable, which was location DESC, and that's the actual name, so I want to call it state name, right? Well, if I try to use spaces here, I'm going to get errors because when you're naming variables, there can't be any spaces in the name, which is kind of why a lot of times what I will do in a lot of data sets that you'll see, anytime I want to use a space, so it makes it clear like this is state name, I just use a little underscore. This is not like, you know, this is just my convention. You could technically have everything run together. It's just a little bit harder to look at. Okay? So now that should go ahead and run just fine. So I can rename variables. I can do other things with the data. But at this point, I've renamed the variables. I don't want to have to continuously go through and file import and worry about file paths. So what I'm going to do is I'm going to save the data, not as a CSV file, but the actual data files we want to use were those .dta. Now, once it's imported it, it's like living on, or you know, behind the scenes as a .dta, but it isn't saved anywhere. So I can save it, and once again, I can use a couple different methods. I can use, oh, that's an and sign. Nope. I can use that file path I've already set up and save it now, same name, but as a .dta file, right? So I'm going to go ahead and kind of save this. And it's now saved it to my folder. So if I now go to my OneDrive folder, hopefully, unless I'm lying to you, I should now have a state cigarette as a DTA file. So now if I wanted to, I can go to my interface, and now it's easy to just nice file and open. What do I want to open? That state cigarette. Notice, oh, it's a .dta file. Stata can now recognize that it can just open that right up. Doesn't have to import it. We don't have to worry about going through the file import. We can just go to file open. And notice this should have my variables renamed, right? That was the one that I saved after I renamed the variables, okay? So quite often with these problem sets, I'm going to give you a DTA file to start out with, so you don't have to worry too much about this. But just to kind of give you a little bit more of understanding of what we're doing, I wanted to walk through that a little bit, okay? So now that I have this data set, yeah.
You have the, so in the file originally, you had it like a different way, not using path, does that still work?
It does if I have the correct file path. It won't in here because I was on a different computer, which is why I wanted to show you that so that I could then tell you if you are bouncing between computers. Generally for you, since you're working off your iDrive, it shouldn't matter as much because you should still always have the same OneDrive path. But just in case you move the files somewhere else, or or you create more like subset folders, you can always go back in and then just change the path.
Okay.
And then your code should just all run right away. So like, let's say, for example, it's a good question. Let's say I have a folder here. Maybe. There we go. And we'll even throw in some weird capitalized, right? So I've got my sample folder. We're waiting. Okay. Once it responds. If I were to like drag and drop that file here, well, now it can no longer find it because it's now under a new file path. So let's say I drag this down here. And I'm going to rename it so I don't have to worry about this capital A. So it's sample folder. Right? So if I try to go back to your point and import that file again, or wait, no, I didn't move the right one. Oh yeah, I did. So if I try to import it now, oh, shouldn't be able to open it up. Why is it able to open it up? Sample folder, fake cigarette tags. There. It might be because it hasn't updated it yet here. So I've got my file path. I think it's because my OneDrive's not updating quick enough that it hasn't created the new folder. But basically, it would give me an error, and then I would just have to redefine my new file path to include that I haven't put it under a different folder now.
Okay.
Right? But that way, I wouldn't have to change every line of code. I would only have to change where I define that path.
Oh, okay, so it's just like, okay, I got it.
Mm-hmm. Like I said, maybe here I can show you in a second. It's just not updating my OneDrive fast enough from creating that here.
So it's like a shortcut, basically?
Mm-hmm. Yeah, it's just not going to update here very quickly. So we didn't have to worry about that. Once again, I've got down here, if you file open, this is going to be kind of this syntax or the code that it runs. So mine is for my desktop. So this shows once again why using these globals is sometimes pretty helpful, because I know that this isn't going to work, right? Because I'm not on my desktop computer. So what will always work, or what I can change later on if I move it, once I have that file path set up, now I can always just open that DTA file that I saved, and notice this is the one that had those variables renamed. Okay? So, usually you'll start out already down here at this line where you're already working with a .dta file, but it helps to kind of have these global paths set just in case you are moving files around, you're creating more folders in your OneDrive once we have more materials, so you can kind of, keep, exam 1 stuff separate from exam 2, or problem set 1 separate from problem set 2. Having this global path line is nice because you can then just go in, update where that new, update the path, and then it'll kind of be able to find those files that you were using. Okay. Any questions before we keep moving here? Hopefully we'll get to some statistics. I know it's a little bit clunky, it's a little bit slow, kind of getting used to using a new program here. Teaching how to use a program is definitely not my expertise in terms of like getting it all set up. Once we have it all set up, it becomes a lot smoother, a lot easier, right? Especially because everyone's got a different computer, web browser, so kind of getting this downloaded and working correctly. I understand it's going to be slow at first, okay? So once I have that file opened up, and it's this .dta file, so it's a Stata file now. I'm working, I don't have to worry about importing ever again. I've got it saved now. It's got my 2 variables renamed. I can also start to do cert commands. Now, generally you aren't going to want to do something like this, but once again, I'm using it as an example for things that we're going to apply to other issues later on in the semester. So there's this variable. There's this command called keep. Once again, notice it turns it blue. That means it's a function that's like stored into Stata. So I'm telling Stata, use that stored command of keep that tells Stata to do a certain thing, right? excuse me, just like when you go to file, save a file, that tells your computer, you're not actually doing the coding behind the scenes. You're using the save, built-in code that's already saved for file save. So we're going to only keep all the observations from this data set. And here we can start to use conditional statements. So we're going to want to do this even when we're looking at conditional distributions, which I thought we might have enough time to talk about today, but it looks like it's probably going to bleed over into next week. But we're going to want to use conditional commands. So like maybe I want to calculate the mean only if the data is from the year 2000, right? Here, I'm just showing you that I only want to keep the data if it's from the year 2000. So anytime you use a conditional command, I can't simply just go keep it if the year is equal to 2000. It says that's invalid. Well, why is it invalid? I don't know, because the way that they coded Stata, anytime you want something to be equal, you actually need to put the equal sign twice. I'm sure there's a reason that computer tech people way beyond my skill level understand, but that is the syntax, right? So here, if I use a double equal sign, it's going to take my original data set, which has what? Years 1970 all the way to 2019. And it's only going to keep the observations that are now from the year. Oh, I think I said 2010. It looks like it was 2000 I had typed in there. Okay. Now, we usually don't want to use this because when you use these keep commands, the data you just got rid of is now gone. It doesn't, it's not like you can call it back unless you reopen the file that you originally started with. So we usually don't want to use these keep commands, but I wanted to use it because it's a nice, easy one to at least show you how we can start to use conditional statements, right? Keep it if this is true, if the year is equal to 2000. And that year, that was saying if the variable year is equal to this value of 2000. Okay. Any questions on that? Now, you can also do a conditional statement. Let's say if the state is equal to AK or Alaska, right? So I look at that state variable. I don't know why I would want to do this, but I only want to keep the observation from Alaska in the year 2000, right? Well, if I try to run this, once again, I'm showing you things, it's not gonna like that, right? Oh, well, duh, you just told me that you need two equal signs, so that's got to be the issue, right? No, right? Because you can use two equal signs and then the number if you're wanting to keep a variable if it's numerical. Notice anytime you have a variable that's not numerical in your data set, Stata lets you know it's not numerical by changing the color. It is red, it is text. I can still use these variables though. It's just when I'm using them in conditional statements, I can't say is it equal to AK, I have to tell Stata I'm using a conditional statement for a text. So it knows that it's text if I use quotation marks, right? So just like when I was using file paths, I was using quotation marks because that was a string of text. Here, if I want to keep only the variable for state being equal to AK, I have to tell it that AK is text. Now, when I run this code, it only keeps the observation that's from Alaska or state abbreviation AK. Okay. Any questions over? It's just getting used to the syntax here.
You run one of these commands, is there a way to get your data back?
So this is a good point. If I were to, at this point, save this .dta file, so let's say I go up here, file, and I save it and overwrite it, I can't get it back unless I get it back from whoever gave it to me, right? So it's not, we don't use this keep command very much in this class. You would do it, it's got other uses, but, generally want to stay away from that because it does just go away. So at this point, instead of overwriting my data, I'm going to go back and open the original data set. So I now have all of it back, right? I was just kind of showing you some of these commands. So we're getting used to some of the syntax, thinking about how we write conditional statements, text versus numerical data. And then one more thing, but that's a good question. Any other questions at this point? Okay. So something else I want to point out that you might be questioning, what is all this green stuff, right? So the way that I would attack my problem sets is writing all my code in the do file. Now you can do that and then write your answers like in a Word document and upload both of them. But I like to do everything in here in my do file. So one way that I can do that is, let's say I had some line of code. For example, we'll do this one, right? So I'm going to use this built-in function of sum, and I'm going to summarize this variable of state tax, okay? So we're going to go ahead, run that line of code, and notice it gives me some output. So what this does is say, okay, in this data set, there are 2,550 observations, right? The mean of the state tax variable is 0.58. It gives me the standard deviation. It tells me the minimum and the maximum. Okay, so I think this must have been tax per pack, or I forget the exact. It's tax something. It doesn't really matter for the concept of what we're doing, but it is some mean tax, right? So if I were to ask you what is the mean of the state tax variable, you would have to know for your problem set that you can use that sum function, summarize that state tax, and to be completely transparent, I think you can use, if I don't type 3 M's here, summarize would give you the same information as sum. It's just, I try to only show you the shorthand because why type out more words than you have to. But if you were to go through the interface, there's ways of doing some of this, and it'll put in like the longer code. But you can always just use sum to find these summary statistics. Now, if I were to ask you this in a problem set, you can't like, I don't want you to be like screenshotting stuff and inserting it into a Word document. So it's probably easier is just, okay, here's the code that found the mean for me. And then next to it, I'm going to add in some words. So I don't want to just start typing things, because now it's going to treat that as code. Anytime I use this like double backslash, now Stata, even if you ran this entire do file all at once instead of like line by line, it ignores anything next to a double backslash. It treats that just as a what we call a comment. So it identifies this is not code. This is just something I want saved in the do file. It doesn't have, I'm not trying to do anything to the data. I just want to put a line of text in here. So maybe there's my answer. If I had this for a data set, I would put the code that would give me the mean, and then I identify from Stata's output what the mean actually is. Now that seems trivial here. Later on, we'll have code that gives us a bunch of output in Stata. And then the actual answer is you have to use some of the things in that output and a little bit of math to come up with what the actual correct answer is.
This is like purely hypothetical.
Mhm.
Could you comment out in the middle of a line and then keep writing in that line? Let's say I did sum and then wanted to comment in the middle.
Oh,
Some state tax.
No, so like, let's say I wanted to do, notice what happens as soon as I put that, everything to the right of it becomes, so you should, that's actually a really good question. You should only ever add comments at the end of that line of code, because anything past that now is green. In fact, if I kind of continue to type, it'll always be green until I hit enter and start a new line. So notice next to these things, there's like different lines of code. 31 doesn't become 32 until I hit that enter. And now it like flushes out. It's no longer that comment that you were just typing on. Is that? And it also makes a little more sense if you have bigger screens where it like doesn't push everything down, right? Just to be able to show it all to you. You can kind of see, okay, yeah, here was my comment. Now I'm starting a new line where I can now start to do, maybe I want to summarize the cost per pack, right? And I can start a new line of code there. Is that what you're asking? Yep. Okay. Well, any other questions before we keep moving here? A couple more things before we get out of here. Go through really quickly. You can also add in this comma detail after you use the summarize command. So I'm going to run this line of code. Notice it just gives you more output. So this does some nice things where it tells us my skewness, my kurtosis, my variance, standard deviation. It gives me some percentile information. So it's just another way of getting a quick snapshot. Imagine like the power of this, right? if I've got 2,550 observations, do I want to do this calculation for the mean and the variance by hand? It's going to take me forever, right? I can find the mean, standard deviation, variance, skewness, kurtosis, all these percentiles like that, right? So it's going to make our life a lot easier in terms of calculating these actual statistics. Okay. All right. So we got 5 minutes left, right? So any questions on that before we keep going here?
So for the instructions on the, that just said pad.
Hmm?
Is that gonna be in the final canvas? Cause I haven't figured out. So I'm gonna get the height of the office.
So this do file's on Canvas, right? So I tried to insert comments like setting the file path, like this is kind of the way that you would do it, right? So when I write these do files, now I don't, this isn't the one because I've added stuff to it now. But anytime I have a line of code in here, I try to add comments that are going to allow you to go back and you're like, oh yeah, what were we doing in class with that line of code? Oh yeah, I was kind of setting my file path. This would be the syntax that I need to use. Okay. But yeah, if you're still running into problems, feel free to reach out and we can try to make sure we're getting things set up so that you're kind of able to open these files and start working with it. Okay. So for the sake of time, we'll pick up next class actually creating different variables. I think this gives us a good kind of look into Stata. We'll finish up some basic summary statistic stuff and then kind of progress towards thinking about distributions. So just to get a little bit of something out of the way for next class, I would take a look. I'll upload the slides for next week. I'll change them to include whatever we didn't cover today, but try to kind of glance through all of this stuff that was supposed to be in this week's, and just kind of, familiarize yourself so the terms don't look completely foreign. It should still be a lot of review, but I want to focus a little bit more of how we do this in Stata, because I know that's going to be the hardest part of this class starting out, especially. Okay. So if you still have some questions, so we're getting those open, we can kind of try to workshop here before the next class gets in here. Other than that, shouldn't be anything on the assignments due or anything like that. Fill out that survey on Canvas. Have a fun, safe weekend, and I will see you guys on Tuesday.